Shane, shall we start?
Yeah, why not?
Okay, it's my great honor and pleasure to introduce Shane Henderson as this week's SNAPP seminar speaker. Shane holds the Charles Lake Chair in Productivity, which is appropriate for somebody as productive as him. He's done research on methodologically, mostly simulation optimization with applications in emergency services planning and transportation. He's an Informs Fellow, recipient of the Wagner Prize, and has had leadership roles both at Cornell and elsewhere, as a former chair of the department at Cornell, as chair of the Informs Applied Probability Society, and as editor-in-chief of Stochastic Systems. Today, he'll be talking about patient survival from out-of-hospital cardiac arrest, and in particular, modeling the impact of community first responders. Shane, take it away.
Okay, well, thanks very much, Daniel. It's really cool to be here. It looks like it's a bit of a quiet week, so we'll just have to do our best here as we go. So what I want to present is work that is not the traditional fare for this group.
Shane, never mind. Now we can see your slides. Go ahead.
Yeah, sorry, I was just sort of doing a little bit of both at the same. Yeah. So what I want to present is not the usual fare for this group. So, you know, I attend a lot of the SNAPP seminars, and I know that our group is very much motivated by, you know, sort of beautiful mathematical arguments, and we're not so invested in the applied part of the applied probability kind of notion. And I feel like that's fine, you know, that's good, but I think we should be bringing new problems into the fold as well. And so that's kind of what I want to do here. I want to introduce a sort of a class of problems that maybe you haven't thought about before. I know that there are a couple of exceptions, like Zeev, I know, is on the line here. Thanks, Zeev, for joining. Zeev saw a version of this talk once before. I'm going to talk about recruitment and dispatch of community first responders. And I'll tell you what those folks are in just a second. There are two aspects to this that I want to focus on. One is recruitment, the other is dispatch. At the recent Informs conference, I gave a talk on this, and I focused more on the recruitment. And today I'm going to try to blast through that pretty quickly and get to the dispatch, which I think is sort of, well, that is our current work, and it's this part that I think you might find more fun. So the players here, the other co-authors are Peter, Ocean, Caroline, and Maggie. Peter and Caroline are faculty members in the Netherlands, and Ocean is one of their former students now, and then Maggie is a PhD student here at Cornell. So what are community first responders? These are volunteers, the people in the community who will augment EMS response for healthcare. So how do these programs work? Well, this very fit-looking person in the bottom left is about to have a cardiac arrest. And just to be careful about terminology, cardiac arrest is different from heart attack. Heart attack means blood flow to the heart is restricted, it gets cut off for a while. That leads to some tissue death and therefore heart attack. A cardiac arrest is just the heart goes into the wrong kind of rhythm. And this can happen to very fit individuals. So you probably heard about the story about the football player over in Buffalo that had this. So that's the kind of thing that we're talking about here. So this person just had a cardiac arrest in the bottom left, and some bystander is going to call 911. So there we get that link going up to the dispatchers and the call takers in the 911 dispatch center. They are going to gather the details of this call and try very quickly to get to the point of whether they should dispatch an urgent ambulance. So cardiac arrest is probably the most urgent type of call that that EMS receives. So these guys will dispatch an ambulance. But at the same time as they dispatch the ambulance, they will activate an app. And that application that they have running on their systems there sends out alerts to a whole bunch of volunteers. And these volunteers on their smartphones have an app that will alert them if they are close to a cardiac arrest. And so here we would alert these three closest volunteers who all have their phones on. This volunteer that's further away, kind of over here, would not be alerted. And then volunteers can choose whether or not to respond. They don't have to, they don't actually have to, right? They're volunteers. This is something that they're just running in the background. And then there'll be some sort of response. And the goal is that somehow we hope that the volunteers get to this event before the ambulance so they can start administering high quality CPR. And when the ambulance arrives, they can do additional things like administering drugs or defibrillating. Some volunteers actually carry a defibrillator with them, believe it or not, and so they can administer that as well. So that's kind of roughly how these systems work. You as a bystander who might have called 911 would also be administering CPR, but if you haven't been trained in this, your CPR is probably not quite as effective as that of some of these volunteers. And these volunteers are typically off-duty paramedics or other medical people like doctors and nurses, can be off-duty police officers, but it could also just be you or me if we've had a course in CPR. So these programs are actually real and operating now. So a long-running one is this thing called Hartslag Nu, and apologies if we have somebody from the Netherlands who can pronounce that much better than me. And so Hartslag Nu has been around for at least 20 years. And originally it was not based on smartphone. It was based on your home address, and then they would send text alerts. But they've been running for a long time. And now, of course, they've moved across to smartphones. Pulse Point is an application that runs in many locations in the US. And it is, again, sort of the same design. The one that we're most familiar with and the one where we have data is GoodSam. So GoodSam was developed in the UK, and now it's running in a number of locations in Europe, the UK, New Zealand, and Australia. And we have data from New Zealand from St. John's Ambulance Service, which uses the GoodSam app as part of their service. There are other versions of these programs. So Lives is a program in the UK, and what they do is, it's a different kind of system. So they're much more like volunteers that just take a shift for a number of hours, and they keep an ambulance in their driveway or something. And then if they're needed, they will dispatch from their home. So it's much more like the rural service. This is more the traditional volunteers that you might know about for EMS. The Red Cross in Norway has been wanting to design one of these apps and has been talking to us about how to do that. And then finally, the fire service in Amsterdam wants to do this as one of their moonshot goals for their strategic plan, but they don't yet have any network of volunteers or anything like that. So anyway, the point is these things are real, but there are sort of questions about how to design these systems, and that's where we want to come in. So the goal of these responders systems is to increase survival rates and also to improve outcomes in other situations. So for the programs that we're looking at, these are only used for cardiac arrest, but there is a notion that you might want to use these for things like trauma at car accidents and things like that. So the ambulances are still going to respond. They're not going to do anything differently. So their workload is about the same. So there's really not any kind of decisions from the EMS side, at least right now, for these programs. And I've already mentioned that I'm going to use the terms CFR, or community first responder, or volunteer interchangeably. Same thing. Okay, so the questions we're going to look at are, what's the impact on first response time and the survival rate from cardiac arrest when you have a certain number of these volunteers? And when you're able to recruit more of these volunteers and you need to put in the effort to do that, where should you be focusing your efforts across a city? A complication in these programs, and this is the thing that really kind of drives my thinking here, is that ambulances will follow direction. And I use this term mostly because you can tell ambulance crews where to go, and they may not always do what you ask of them. But anyway, they mostly are under centralized control. But the volunteers, they just do whatever they like, right? They live their lives, they do their own thing. So how should we model those volunteers? And there's a lot of them, right? So you're typically talking about 5,000 to 10,000 in a middle-sized city. So the too long didn't read on this part is that we're going to model the volunteers using Poisson point processes, and that's going to enable us to use convex optimization to sort of determine recruitment goals, and the like. And the second question is, how should we be dispatching these volunteers? And there's a sort of a, what do I mean by that? For survival for just one cardiac arrest, you should dispatch everybody who's close, and that would be good for that particular patient. But if you're a volunteer and you arrive and there are 5 people there before you, you are not going to be needed, and therefore you're going to be a little bit frustrated that you received the alert. And so maybe you shouldn't alert everybody who's within the circle. Maybe you should do some kind of time staging. So we'll talk about that. So that the too long didn't read on that part is that the natural inclination for our community is to use stochastic dynamic programming. And what I'm going to show you, or what I'm going to hopefully convince you of, is that that's not necessarily the right way to go, and that we might be better off with simpler tools which relate to the use of decision trees and simulation. So the natural inclination here may not be the right one. Okay, so what I want to do is first talk about recruitment. And so let's sort of look into that. So here's a map of Ithaca. And let's say I am down here in the downtown, college town kind of area. And so this is pretty close to the Ithaca campus. And let's say that I end up with a bit of a problem. I am at the center of this circle and I've just had a cardiac arrest. And so what will happen is I will look in maybe some radius. These apps will look in some radius of that cardiac arrest. And those radii are determined just by latitude and longitude. So they ignore natural barriers like this river that's flowing up here. And if there are any volunteers in that radius, then they will be alerted. So on this particular day, there happen to be volunteers in these positions. So I'm indicating them by little halos because I think of them as angels. And here I have 4 people that are all pretty close who would all receive this alert. These people outside the circle would not. On a different day, you might have volunteers in a different set of locations. And again, you get a sort of a similar sort of thing happening. So all of those people, at least in the way that we're talking about it right now, in that shaded circle would receive the alert. So the way that we're going to model those guys is those little angels is we're going to model them as a realization from a Poisson point process with some mean measure. And that mean measure we could just write down as some single expression, but I'm going to break it down into these 3 components. There's going to be N, alpha, and nu. And the way to think about these is that N you can think of as the number of volunteers you have in the city. So think about that as maybe not for Ithaca, but think about that as in a city like Auckland in New Zealand, which has about 1 million people. Think of that as about 5,000 to 10,000. Each of those volunteers will accept an alert with a certain probability, and that I want you to think of, that's this alpha. In New Zealand, that fraction is about 0.17. But in London, in England, that fraction is more like 0.5. So there's some pretty big differences from location to location with this probability. And finally, once we get through to this last expression, this nu, what is that? Well, that is a density over the city locations. And we're assuming that these volunteers are IID and have this density for where they're located. So the consequence of this model is, if you're using a Poisson point process, is that the number of volunteers in any fixed set B is Poisson distributed, and we can write down its mean. Okay, and that means that we can compute the probability that there are no volunteers in that set, and that is this e to the negative whatever, right? This is just a Poisson probability of seeing 0 events. So these kind of calculations are easy and standard once we have the raw ingredients N, alpha, and nu. So why is this the right model to think about? And I think it's important to just briefly mention this. It's a convenient model. It's mathematically nice, but why is it sort of the right model in the setting? So we've got a bunch of CFRs or volunteers. And if we assume that they're not colluding with each other in any kind of interesting way, then each one of them has a small probability of being in that circle that I've just positioned in the city. So if I condition on the location of the cardiac arrest, that's a deterministic circle from the perspective of the volunteers. And so now the number of those volunteers in the circle has a binomial distribution. The binomials with large n and small probability of being in that circle, that's approximately Poisson. And so we're going to model the number of volunteers in that circle as being Poisson. And in fact, their locations as well, we're going to assume have some sort of uniform density. So this is just by way of motivation, right? But you might say, well, each volunteer lives in and spends their time in different parts of the city, and that's fine. If each volunteer has a different probability of being in that circle, there's something called Lecam's theorem, and it tells you that the total number of them in there still looks approximately Poisson. And if you say, well, wait a minute, each one really just has a oh, I'm sorry, I've sort of crossed my wires. But anyway, you get the point. Even if the volunteers have different location distributions for where they live and spend their time, there's something called the Laplace functional, which you can use to establish that this thing is still approximately Poisson. And this Laplace functional is basically just the sort of equivalent notion to a moment generating function, but it's really applied at the stochastic process level because you're looking at a point process, not just a real valued random variable. So anyway, you can sort of this slide should really just motivate you that this is probably the right model. So if you then use those ideas, you can compute the cumulative distribution function of the response time as a function of the different densities of the volunteers. And this is there's nothing fancy going on here. This is no surprise at all to somebody who's played with Poisson point processes. So let me just sort of indicate something in this picture. So on the horizontal axis, I have the response time of the volunteers. And on the vertical axis, I have the probability that the response time will be less than, whatever that threshold is. So these are just cumulative distribution functions. They all emanate from this number 3. So think about 3 minutes as being sort of the time that's required to at least notify these volunteers. It's that time from patient collapse to the call to the 911 call center, plus the call taking time before they realize what's going on. So you can't beat 3 minutes in this study. And then as we increase the density of volunteers from 0.1 up to higher values, these CDFs sort of lift up and to the left in the plot. So it's a very natural model that I think is sort of doing all the right things, right? These are all calculations that are very straightforward. So we can now get the response time of the volunteers. And what we want to do is combine that with information on survival probabilities to get an overall survival function. So here's what I mean by this survival stuff. So on the horizontal axis, again, I have that response time from cardiac arrest to arrival of the volunteers. And on the vertical axis, I have the probability that the patient's going to survive. And these are all different curves that come from the literature. And I stole this picture from this paper by Erkut, Ingolson, and Erdogan. So they were looking at survival using just purely ambulance response, but these curves were in the medical literature and have been for some time. They're mostly based on logistic regression kind of fits to data. And so I think I'll just sort of skip over the details of where they come from so I can keep moving. But we can take this curve and then we can combine this survival probability function with the response time CDF that I just showed you that comes from the Poisson point process modeling. And once we've got those two things combined, we can compute survival probabilities overall. So if we do that for something that's sort of semi-realistic, here's the city of Auckland in New Zealand. Just by way of scale, from the top of this picture to the bottom, that's about 40 minutes driving, maybe a bit less than that. And the city center is right here. There's a bridge that cuts across the harbor here, but that's not shown in this map. So we make some reasonable assumptions here, and the densities of of population and things do vary in this map according to the color coding you see. But anyway, we take all that stuff into account. We position ambulances using a sensible model called MEX-CLP, which is a method devised by Mark Daskin a long time ago, but it's still considered one of the top methods for doing this. So we just position ambulances according to some sort of realistic deployment, and then we try to do some calculations. And you end up with plots that look a little bit like this. So here I'm assuming a fixed number of volunteers, 1% of the population. And what you're looking at is I'm varying alpha. So alpha is this acceptance probability. So when you get the alert, what's the probability you'll actually accept? And I'm varying that over a considerable range. And so this is going to change the density of volunteers that you see who could accept the alert. And then you get these predictions, right? So we can look at a traditional measure that EMS is measured by, which is what's your fraction of late arrivals, meaning, so you have a time threshold, say 12 minutes or 6 minutes. What's the probability that your first response is outside that time frame? So for 12 minutes, you see that this almost immediately plunges to 0 with lots of volunteers. And that's just because with even a modest number of volunteers, you can get to that patient easily within 12 minutes. But for the more stringent measure here of 6 minutes, which is both of these thresholds, by the way, are used by EMS in Auckland. For the more stringent 6-minute target, you have to work harder to meet that. So you need a much higher density of volunteers or a much higher acceptance probability. So that's on this side. But what about from the perspective of survival? Well, even without any volunteers, you have some ambulance response, and that will give you about a little bit less than 10% survival rate. And then with volunteers, you can increase that survival rate, but you can see that this is increasing pretty slowly. It's much harder to get those survival rates way up. So these kinds of plots are super useful for us when we're talking to the Red Cross or to that fire department in Amsterdam, because they're interested in having these programs. They don't have a volunteer base right now, and they're wondering how many volunteers they're going to need. So we use plots like this to help them. But then I mentioned recruiting, and this is sort of where we've been thinking more in this space. So when you have a certain number of volunteers, from where should you try to recruit them? And the difficulty here is that when we're recruiting volunteers who live in a certain area, they actually spend their time across the city in other locations as well. So that location probability distribution does vary depending on the time of day. You know, at night, you're mostly at home. During the day, you're at work. So we use what we call profiles to try to model that. So the idea is...
Shane, can I ask you a question before you go into the profile definition?
Please do.
Going back 2 slides to exactly the slow growth of the survival probability, how should one think about the cost-benefit analysis of such a program? Like, maybe in different words, increasing this from 0.1 to 0.15, would that be a huge win, or would that be considered sort of like saves maybe 1 life every 3 years and is not worth the resources? Like, how should one think about that number in terms of expected actual number of lives saved, in terms of cost of such a program? Is there some way of thinking about the relative benefits here?
Yep. I think I understand. Thanks, Daniel. Yeah. So we in more recent work, we're measuring everything in terms of lives saved per year. And if you wanted to go to a sort of a quality adjusted life year, you know, there are various estimates for that, and you get into the whole conversation about death panels as soon as you bring up this deal. But I mean, that's sort of one way to do it. So if you're sort of familiar with quality adjusted life year analysis for different health benefits, I think I'm going to get the number wrong, but I think it's something like 50,000 pounds or something on that order per quality adjusted life year. So if you save, you know, if sort of even just a handful of lives, you're in business. In New Zealand, I'm going to probably get this number not quite right, but I think it's something like a couple of thousand cardiac arrests per year. And we're making a difference here. You can sort of see the difference in the survival rates, right? So that gives you a sense of how many lives you're saving. And therefore, by mapping that through qualities, you would get some sense of the impact. I hope that answers the question.
Yep. So a different way of answering is a 0.05 improvement is huge.
Oh, absolutely. Sorry. Thank you. Yeah. We're pretty excited about going from 0.09 up to like 0.13, 0.14. That's huge. And then beyond there, we want them, it is additional lives, but it's diminishing returns. Yeah. Cool. Okay. So back to these profiles for a sec. So these are just where do people spend their time? And you can think of it as a bunch of stochastic matrices. So for each time, think of that as like a time bucket, right? Weekends during the day, weekends at night, whatever you like. If you've been recruited from location J, then where are you spending your time? We're going to put that in this in the I index. This is the wrong way around for typical stochastic matrices, right? Like typically the rows are summing to 1. These are columns summing to 1, but it's the same idea. And we're going to just ignore time. And that's really just for clarity, because you can see I'm just conditioning on time here. So time is not really the critical thing. We just basically you do repeat the calculations for different times of the day. And now what do? Well, we look, where do people live, and then where do they spend their time around the city? So this is estimated from census data. I won't go into the details right now. So we can estimate for somebody who's been recruited from who lives in the central business district, where do they spend their time? And most of them spend their time in the CBD, but they do spread out a bit. And then you can also look at things like inverse profiles. So where do people come from who are spending time in the CBD? But again, I'll just skip that. So now what we do is we say, well, what are the decisions that we're making? It's how much effort we put into recruiting people from the different, who live in the different regions. So this X vector is going to be my decision vector. It's what fraction of my effort do I devote to recruiting people from each of these area units here in Auckland. There's 287 of them. And so I just have to satisfy, I have to lie in the probability simplex for that. So, and then what I do is I take that decision and I map it through my profiles to get where are people going to spend their time, right? So this new is where people are actually, and the X is where I'm recruiting. And the X is my decision vector, and the new is what I get. And now I just plug everything else into my previous analysis. So here we get these optimization problems. So we've got this constraint that links effort to allocations. We have our probability simplex, and then we have an objective function, which can be any of a variety of things. So if that objective function is just the probability that your response time is greater than some threshold, then it turns out that this is a convex optimization problem. And so that means we've got lots of tractability here. So it's sort of easy to solve these problems. And it turns out that still holds. And if you look at this objective function being the death probability, then again, it turns out this is a convex problem. And finally, if you have a more complicated kind of modeling of survival here, where you take into account time to CPR and the time to for the EMS to arrive, those are two different times, with the time to EMS potentially being the same thing as CPR if ambulance is the first response, not volunteers. So you basically have these two response times. Then it turns out, again, under basically assumptions that no one would argue with, this is still a convex problem. So that means we can use some kind of convex optimization methods, and we use Frank Wolf with away steps, and we can solve these problems very easily. So when we do that, we get results that look a little bit like this. And here I'm showing you two different optimal solutions. The one on the left is when you optimize for late arrival, and the one on the right is when you optimize for survival. And I think the main thing to notice here is the really quite different solutions. On the left, it's much more of a uniform kind of allocation that you're pursuing. And on the right, it's much more concentrated. And there's interesting effects that happen around the ambulance bases, which are these funny little circles. So I won't go into the details there, but basically the solutions look really different depending on which objective you're optimizing for. If you look at what are those solutions actually looking like? So let's suppose that we're trying to optimize for survival. You might postulate that the right thing to do is to just allocate volunteers in proportion to the demand. And that's not true, but it's almost true. So here on the horizontal axis, I have something like demand, it's demand density. And on the vertical axis, I have allocation of volunteers density. And you get these kind of interesting curves. So if the optimal solution, here I'm ignoring the profiles, and I just imagine that I could figure out how many volunteers I wanted in each region. So if the target thing to do would be to just allocate proportional to demand, you would have everything concentrated on the line, the diagonal line here. That's not what we're seeing. We're seeing these curves that sort of come across for a while and then sort of concave increasing here. So what's happening here is basically, if you have a region that doesn't have very much demand, just don't even bother trying to allocate any effort there. There's no point recruiting from there. It's not going to make enough of a difference. Instead, what you want to do is sort of allocate more to the places that have higher demand. But as the number of volunteers that you have increases, and here we went kind of berserk with this very high number, this sort of orangey yellow color. Basically, you do allocate some effort to everywhere, and in fact, you over allocate to the quiet ones. But then you sort of reduce how much you allocate to the busier ones. So these kinds of curves should be familiar to you if you sort of think about queuing kind of effects. But there's no queuing going on here. It's really more about just getting that density up sufficiently. And for these larger demand density areas, eventually, you sort of you're hitting the diminishing returns on those survival curves. So you're not getting much gain from adding volunteers there, so you add them somewhere else. So anyway, this kind of curve gives a lot of intuition, and it also sort of indicates why proportional, which is much more intuitive to the people that we talk to, is really not bad, right? It's pretty close to optimal. So we've already kind of said this. So getting the density of volunteers proportional to demand is not optimal, but it's close. And the recruiting can be a bit subtle. So for example, we don't actually recruit from, in some of our optimal solutions, we don't recruit much from the central business district. And that's because it sounds a bit odd. Like that's the place where, where people are having the most cardiac arrests, but we don't actually recruit from there. And the reason is that you have all these other people in other districts who commute into the city. And so they're present at the time that most cardiac arrests happen. So there's not much gain to recruiting from that city center. You've already got lots of volunteers there when the cardiac arrests are happening. So a couple of other quick thoughts. It turns out that this kind of model does work well mathematically with the models that we use for optimizing for ambulance locations. So if you wanted to do something like modifying your ambulance allocation to take into account these volunteers being present, you could do that. That would be fine. But nobody is doing that right now because cardiac arrest is a small fraction of the ambulance or EMS demand. So that's sort of more like a hint for the future, maybe. So we do make a difference. It makes a huge difference in terms of the survival rates. So going from 0.09 up to 0.14, 0.15, sobering, but that's still, more than, you're sort of, the improvement in survival rates is more than 50%. So that's a big deal. But this acceptance probability, this is kind of key. It really drives a lot here. So I haven't shown you any data. And one of the reasons for that is that cardiac arrest is a rare thing. And so you can't just do everything based on data. But basically what I'm just going to say is the models that we're using look to be roughly consistent with what we see in data. It's not a perfect match. Like in a perfect world, I'm not going to explain it, but in this right-hand panel, that sort of indicated curve should align pretty much with these bars. And it's not that great, but it's also not that bad either. So this is kind of something we would sort of like to working from the data. There's just not enough of it to really drive these decisions. Okay, that brings me to dispatch, but maybe I should pause again just for a sec. Okay, I'm going to bang on. So this is the part where I feel like we're using some techniques that I think you could find useful in your work if you're doing any of these kinds of dynamic, any kind of situations where you're thinking about using stochastic dynamic programming. I think there are some ideas here that you might find interesting. So here what's going on is we're given a single patient, right? And we're going to observe some stuff, and then we're going to make some decisions. So this is a different context from what we were just talking about with recruitment. With recruitment, where we're thinking about a bird's eye view across many, many cardiac arrests. And here we're zooming in on one. So what happens here is we get a single patient. In the application, we observe the location of the patient and the location of nearby volunteers. So we know that stuff. We also have a pretty good idea of how long it's going to take for the ambulance to get there, because we know where the ambulance is being dispatched from, and we've got lots of experience with ambulances getting there. There is still some randomness in that response time, but it's not that big. So we know these things. So we need to decide who should be alerted and when to try to maximize the survival probability for this patient. But at the same time, we want to avoid volunteers from being annoyed because they get too many alerts, or we're going to try to avoid volunteers from being annoyed because they show up on site and there's 5 people in front of them. So the fatigue one is really quite prospective. This is not really a big issue right now. So you don't tend to get fatigued from alerts. Sorry, that's what I meant to say. The alerts is not the big deal. And that's because you're only getting about 2 alerts a year. So if you're only getting 2 alerts a year, it's not a frustration for you right now. But if you are if you're showing up to these things and there are a bunch of people ahead of you, that is annoying. So I think we should probably keep in mind that it's this redundant volunteers, this second objective that we're forming down here, that's probably the more important one from practice. But both, I think, are interesting, so we've included both. So the number of alerts could become annoying if they were to extend the service beyond cardiac arrest. So here we combine these objectives into one using the usual sort of tricks of putting in a multiplier on one of them and just taking a linear combination. And now we're in a situation where we can try to work with this single objective. And so that's what we're going to do. We're going to look at a dynamic program where we're going to minimize, by choosing the alert times for our volunteers, we're going to try to minimize that overall objective function. And you have these, you might have these 2 different situations that I've depicted up here. The red dot is where the cardiac arrest happened, and then these greens are your volunteers. And in this first one, you might do something quite different from the second, because you can see how the volunteers are all quite a long way away in this second setting. So, maybe you want to do things a little bit different in these 2 situations in terms of who you alert. So the basic idea is we're going to solve a dynamic program. And we're going to stage the alerts. So we're going to alert some people, we'll wait for a bit, see what happens, and then we might alert more as we go. And that way we won't get a whole bunch of redundant people showing up. So the setup, if we just do this computationally, is we'll have a 5-second increment. We'll have the time horizon is the time when the first response happens. So that's sometimes when the ambulance arrives, or it could be when the first volunteer shows up, whichever one happens first. And then we track which volunteers have been notified or have rejected the alert. And the things that we can do in this dynamic program, our actions are do nothing or notify the next closest. So you notice here, I'm saying next closest. That's because, a simple interchange argument tells you obviously start from the closest volunteer. I say obviously, and that's because we don't have a lot of information about the individual volunteers. But if we had information that said that some volunteers were more likely to respond than others, that would break this obvious interchange argument, and then you might do something a little fancier. When I gave this talk at Informs, I think it was there, Zeev had this nice observation that you might do different kinds of alerts to different people, but let's push that off just for one sec. For now, these are just, you either alert or you don't. It's one kind of alert. Okay, and then the rewards are sort of natural things. So here's what you get from the dynamic program. So you get a sort of a nice concave frontier. So that's probably the first observation here, but what's going on? What I'm doing is I'm taking, I should clarify, I'm taking a single instance of a cardiac arrest, and I have volunteers that are a certain distance away from this person, and then I'm just, to get each of these different dots in this plot, which I'll explain in a second, I'm just varying that gamma parameter, this guy up here, and my objective function here is penalizing the number of alerts, and I'm assuming that I have a fairly high acceptance probability up here. And when I set things up in this manner, and then I just solve the DP a few different times for each of those different gammas, I trace out each of the dots in this plot. And this red X is what we've been told is the current policy at with the Good Sam software. That's what it would achieve. Now, there's something a bit weird there, because we've been told it's a policy of a certain kind, but when we look in the data, that's not what we're seeing. So it's a bit confusing there. But anyway, this is what the frontier looks like. And I think I just want to point out a couple of things. Do you see how this left-hand scale ranges from 0.04 to 0.18? So we can, if you don't do any alerts, this is actually particularly bad in this area. This is a very poor situation for ambulance response. And then, but you can really get that survival probability way up here by getting this volunteer response up. And you can see how there's diminishing returns, as you would expect. Okay, so just keep that in mind for a second. This is with a probability of acceptance of 0.5. That was like the London situation. But if I move to Auckland or New Zealand in general, where it's much lower, and we don't know why, by the way, then you get a plot that looks like this. There's less fill-in of the dots. And moreover, you can see that the vertical scale here is dramatically lower. It's only going from 0.04 to 0.07 now. And this is kind of what you would expect, because we're penalizing you for every additional alert that you make. And the probability of acceptance is very low. So you're not getting much bang for the buck. And therefore, these dots where we're sort of alerting people, there's not a lot of spread, because you're not getting, after your first dispatch of alerts, you're not sending many more because it's so expensive because of the form of this objective. So you're sort of getting poorer quality there. If you instead are dealing with the number of redundant people who show up, then you get what look on the surface like similar curves, right? Not concave and sort of fill in here, and we're back to a high acceptance probability. But I want you to notice this vertical scale, right? It's now much more compressed towards the upper end. So you can get very high survival probabilities, and even with a modest number of response. So it's a lot better. This 0 here, by the way, is the number of redundant volunteers on scene, right? So this means that you did have somebody who responded. That's why you're actually getting a better survival probability. So redundant seems to compress the vertical scale. And if you think about it for a bit, it makes sense. Similar sort of story with lower acceptance probability, but I'll just sort of maybe skip that one. So if you actually look at the policies themselves, then they sort of bring out some sort of interesting aspects. So here, what I'm going to do is I'm going to solve for the optimal policy in a bunch of instances. So I'm going to solve many dynamic programs, and I'm going to get lots of points. And then I'm going to look to say, okay, did I alert certain volunteers at time 0? So here's a bunch of different instances, and I looked at, did I alert the closest volunteer? And 1 means yes, I did, 0 means I didn't. And if you look at the time for that closest volunteer to reach the patient, there's a pretty clear cutoff. Basically, you do alert this person up to a certain point, and then you cut it off. So this kind of makes sense, right? You would, if the volunteer is too far away, they're not going to be able to help you in any material way, so you don't alert them.
Shane, can you clarify one thing? Do you have new people arrive over time, or are the volunteers just fixed?
Yeah, the volunteers are just fixed because on the time frame that we're looking at, things are too slow.
So why would you, if you were minimizing for redundancy, would the same thing for redundant volunteers, would the same thing hold true, or would you just always alert at least one person?
I love the question, and I'll get to there in just one second.
Sorry.
No, it's fabulous. I'm glad you're asking that question. It means you're thinking ahead, which is great. So we're still just penalizing alerts here, right? So you see a sort of a pretty similar cutoff behavior here with the second closest and so on. So it's all pretty natural here. It's expensive to alert these additional volunteers, and so there's a sort of a distance thresholding that happens. But when you get to the redundant, it's quite a different story. So here is the closest volunteer, and of course, you're not penalized for that closest volunteer, right? Because they're not redundant. So you definitely alert everybody. But then what about the second closest? And this is Daniel's point. Here you see this kind of overlap, right? So there's a range of distances where sometimes you alert them and sometimes you don't. And that's going to relate to what happens with the outcome. Like, did that first volunteer cancel the alert or not? So it's quite different. And the same thing is true, and it's even extended for the third volunteer. So there's more of this sort of complexity and overlap here. And it's really just because we're penalizing redundancy. So once you get somebody declining an alert, then you can start, alerting other people for no cost. So it's quite a different setup. So the DP, you can prove some stuff, but these are all pretty sort of one-line kind of things. You dispatch from the closest to the farthest. That's just a simple interchange. If we had to assume Markov everything, right? So everything's exponentially distributed, all that kind of stuff. So from that perspective, you would only issue new alerts when one of your alerted volunteers declines. So that's the second point. And that's just the sort of usual Markov property for policies. That efficient frontier is concave, and that's because you can always take a mixture of two sets of actions, and that will be something you can do feasibly, and it will fill in the sort of lines between dots. But the optimal policy is better than that. So it pushes up, and therefore that tells you that the efficient frontier is concave. And then we have a partial result. It's not the one we actually want, but it's when should you not bother to dispatch CFRs at all at time 0. So we have a coupling result there, but that's not quite the one we want yet. So I'm going to skip over that. The DP is really slow. So we can solve up to about 7 volunteers pretty quickly, but beyond that, it's getting super slow. And it's assuming exponential everything, which is annoying because those times are not exponentially distributed. So here's a histogram of response times for volunteers. And what you see is that it builds to a peak in about 30 seconds, but then it tails off, and you still have a significant number that are still potentially going to respond after about 2.5 minutes or something. So you've got this kind of shape for these responses. These folks out here, out near 10 minutes, they're pretty much useless for survival, but this is what you see. So there's another approach that you can use, which I think this is something that I think you could use in your own research. And this one says, okay, well, what could we do here? Let's enumerate a bunch of policies. So, for example, what could I do in my situation? I could, policy number 1, send everybody who's within the radius, and that will have the maximum survival probability. I could instead send 3 people at time 0 or 4 people at time 0 and then be done. Or I could do some kind of staggered thing where I alert a bunch at time 0 and then alert additional people every whatever seconds. Or I could do this keep n. That means as soon as somebody rejects, I alert one more person. But there's many other policies you could use here, and we're looking at more fancy policies these days. So anyway, this particular set of recipes gives you about 40 different policies that you could consider. We're not going to just pick one of these policies, though. What we're going to do is we're going to apply a policy to a particular setting or a particular scenario. So a scenario here is, how far away are these volunteers? So one in this picture, one is at 55 seconds away, one's 100 seconds away, one's 103, and so on. So this is a scenario, and that's information that we know at time 0. And then what we're going to do is we're going to simulate every single one of these policies on this particular scenario, tracking rejection times and how long it takes for people to respond by bootstrapping from the data. So we're actually just drawing from the data that we have for this. And so that makes it more realistic because we're capturing things like dependencies and so forth. And what we can do is we just evaluate every single one of these policies on every single one of, say, 3,000 or 4,000 scenarios. And then what we know is the optimal amongst our set of policies thing to do for each of these scenarios, right? And then finally, we're going to do some classification where we just try to classify the scenarios according to what would be the optimal thing to do. And that could be a decision tree or a cart or whatever you like. But what we're going to do then is we'll have that decision tree or that classification method, and we can then apply that in real time. So when a call comes in, we observe what scenario we have, how many volunteers, how far away they are, and then we can look up in the decision tree or the classification method which strategy or which policy we should follow, and then we can use that. So that's basically the idea. It's a very simple idea that enables you to get approximate solutions to dynamic programs that are quite effective. And you can include current practice, you can include sort of ideas that are intuitive to other people. And if you do this, you get trees that look a little bit like this. This is just a simple result. We've got more complex trees these days. But the numbering here, CFR4, that's the 4th closest volunteer. Is that person less than 7.4 minutes away? If the answer is no, then what about the 3rd closest? If the answer there is also no, then you only send 2 volunteers at time 0, and then you're done. If that 3rd volunteer is close enough, then you'll send all 3 at time 0. That's kind of how to read this tree. And then if you go down the left-hand side, you do the same sort of thing, and you can see that you have slightly different policies down here at the leaves. And we will know immediately upon receiving a call which of these situations we're in, so we know which of these dispatch policies to pursue. And the nice thing about this tree thing is after we've trained it, it's instantaneous to run, right? It's sort of super fast. The question is it any good, right? Because we've only drawn from a finite number of policies. Well, this we're still trying to figure out. We're still trying to come up with duality results that tell us how good these are. But here's some evidence that these are pretty good. So what we can do here is we replace all of the realistic response times with exponential everything, and we do the same training. And then we look at what the decision tree policy's survival probabilities are versus what the dynamic programming policy would be, because we can solve for the dynamic programming optimal policy. And these numbers are small in survival probabilities here, because this is just with a few small number of volunteers, so we can solve the DP. And what you see is that for each instance, which corresponds to a dot, we're pretty close to diagonal here. There is a little bit of vertical separation, which we actually do care about. It's, even though they're very, very small numbers, it does translate to a few lives a year, but we're pretty close to optimal. And so this is telling us that this approach is not bad, at least if you assume exponential everything. We don't have evidence of how good this approach is when you don't have that exponential assumption. So I guess the main thing here is that the dynamic program and these decision tree kind of policies, they kind of don't intersect, but they're useful. Each sort of complements the other in ways of thinking about it. This approach is, we really just sort of adapted this idea from this paper by Van der Hagen et al. But this idea has actually shown up in a number of different places. So the place where it's closest to my work is in this contextual ranking and selection and simulation. I mentioned we don't have dual bounds, but we want to get them. And we're still sort of getting going on this dispatch stuff. But it seems to be of great interest to the folks who design these apps. So some other things that we would like to do is we'd like to try to figure out how we can boost that acceptance probability, because that's basically like increasing the number of volunteers you have. We may not be the right people to answer that question, but we want to try to at least think about it. What happens if you dispatch to other kinds of incidents? So I mentioned trauma. That could be interesting. I mentioned that the program in the UK doesn't operate the same way, but can we use some of these same techniques? And I guess some of these other ones are a little bit more flaky, but let me just mention this one. So I have been talking to people at Lyft about whether drivers might carry AEDs in their trunk, but there are issues there. You know, like if you have to actually pay drivers to respond, because after all, they're trying to make money, how much should we pay them for that? And that might bring us into conflict with Good Samaritan laws, which say that if you're, if you're responding with good intent, you're not liable if something goes wrong. But if you're being paid for this, it might be different. And there are other application settings, but maybe I'll just skip that here. So I guess I'll stop there, and thank you for coming today.
Thanks a lot, Shane. I knew this was a ride-hailing talk at heart. Do we have questions from the audience? Maybe before we get to questions, a quick announcement for everybody who's still here. We'll have 2 more SNAPP events this semester, not 1 more, but 2 more. One is our last regular seminar, happens in 2 weeks with Hong Nam Kung speaking from Columbia. And the second is that on December 11th, so 3 weeks from now, we will have a lightning talk session, and details will follow about the speakers we're going to include and the exact setup for that. Do we have questions for Shane? Either in the chat. There weren't any in the chat during the talk.
Yeah, well then thanks, Daniel, for being curious. That's great.
I think Ziv has a question.
Yeah, I've got a few. I mean, I can walk all the way to your office and ask, but maybe here's one. So I was thinking about the sort of decision tree approach, and at the end of the day, you end up narrowing down to like one policy. Is there value in using a decision tree to narrow down to like the top 2 policies? Or is it the case that the top 2 policies are close enough that you should just pick one, that even the 5 seconds of simulation wouldn't be worth it?
Yeah, thanks, Steve. So it's true that at each leaf of the decision tree, we do narrow down to one policy. So where the ultimate thing that you do ends up being a mixture across all of these different policies of those options. I'm not sure that there's value in narrowing down to a couple of policies at each leaf, but there are certainly different ways of doing classification where you're aware of the loss that you're making when you're making each of your decisions. And I feel like that's how your idea would play a big role. Yeah, thank you. Yeah.
Ziv, do you want to ask another one?
I'm good. I mean, I can come up with more, but I should.
Yeah, thanks, Steve. Steve was great when we had this Informs presentation. You're super imaginative.
Shane, let me ask a few, and one is very practical, I think. I imagine a volunteer showing up to the situation, but it's not like the situation has necessarily a big flag and it's visible everywhere and marked with signage. This is where the person had the cardiac arrest. It's like you show up on a street and the GPS maybe works or doesn't, and you're trying to find it. I'm wondering, is it actually, like, as you think about the redundant volunteers, I feel like there's sort of like beyond the 5th, it's clearly redundant. The second one might actually be helpful because you do shave off 30 seconds there in who's actually getting to the person. Is there, do you think the results would at least directionally all hold true if you were okay with 2 people, but at 3 you only start penalizing redundancy?
Yeah, I think yeah, it's a very good point. I mean, certainly even beyond what you've just described, you do need two people to do CPR for extended periods of time. So it's sort of hard work. Yeah, everything it just goes through. It's yeah, so you can put a different threshold in there and it's just fine. Your point about making it can be hard to find the patients. That's certainly true. Usually what happens is the dispatcher at the ambulance call taking will keep the person on the line and say to them, the person who rang, and say to them, make sure that you find somebody locally who can run out and help people find the patient, right? So if you're in your home or if you're you're in a restaurant or something, somebody will be sort of told to do that. So it's not as much of a problem as you might think, but it does still happen, and so it is worthwhile.
Makes sense.
Yeah, thanks for the question.
Do we have other questions from the audience? If not, then let's thank Shane once more. It's been a fantastic talk, as one would expect from you, and hope to see you around soon.
Yeah, thanks very much.
And Shane in particular.
Yeah, well, thanks for coming, folks. I know this wasn't the usual sort of math thing, but I think more modeling kind of stuff is good for us. Cool. Okay, thanks all. Thanks, Daniel.
My absolute pleasure.
Okay, see ya.